All right, now we're going into Chapter 7, and one could argue that Chapter 7 is where the real organic chemistry begins. What we've been doing in Chapters 1 through 6 is kind of getting the background material, getting us used to the stuff that is organic chemistry, some of the types of molecules and some of their properties. Now we're going to start to get into the reactions. We're going to use all that information we learned in 1 through 6 and apply it to organic reactions. The first reactions we're going to do are nucleophilic substitution reactions. And to start off with, we find that most of the time when we're doing nucleophilic substitution reactions, we start with an alkyl halide. And we've already looked at these. We've got methyl halides. This would be a primary alkyl halide because there's a CH2 bonded to chlorine. Here the chlorine is bonded to a CH, so that's secondary. Here the chlorine is just bonded to a quaternary carbon, and so that's a tertiary alkyl halide. And these are the main types of molecules that are going to undergo these nucleophilic substitution reactions, at least we're going to talk about in this chapter. You will also find allylic halides, where you've got a double bond and a CH2, or a benzylic, where there's a benzene ring, a phenyl group, and a CH2, and then our alkyl halide, then our halogen. Those will also work in these reactions. Vinyl and aryl, if you don't have that CH2, if you don't have that extra carbon here, vinyl and aryl alkyl halides will not work. All right, nomenclature. Good news. We've already been through the nomenclature of alkyl halides. We covered that in Chapter 4, so we don't have to worry about that, but here's a little bit of a refresher. Physical properties. The main thing to note is the CX bond is polar. The carbon-halogen bond is a polar bond. The halogen is more electronegative, and so the halogen is going to have a partial negative charge, and the most important part is that gives the carbon the partial positive charge. And when you have this type of situation where you have an alkyl halide, what we find is we can do substitution reactions, and in Chapter 8 we'll look at elimination reactions. Substitution, if you have an R group, just a normal carbon-containing group with an alkyl halide, if you react it with a nucleophile, something with a lone pair, possibly negatively charged, we will substitute the nucleophile onto the alkyl group and kick off that halogen. All right. Now that is on nucleophilic substitution. In Chapter 8, we'll look at elimination, where a base can come in and take this proton here, and then this leaving group, this X halogen leaves and making a double bond. Worry about that in the next chapter. Right now, we're going to focus on nucleophilic substitution. And here's the general gist of it. If you have an sp3 hybridized carbon bonded to a halogen, we call this halogen the leaving group. Prime leaving groups are the halogens. We're going to find in Chapter 9 that water is a good leaving group. A nucleophile, you have a lone pair of electrons on here. Often nucleophiles are negatively charged. They do not, excuse me, they do not have to have negative charge. Okay, a pi bond can also be a nucleophile in certain cases. So our nucleophile has got a lone pair, and this lone pair is going to be attracted to the partial positive carbon of the R group due to the RX bond. And so the nucleophile will attack this R right here. The lone pair will attack this carbon. We'll draw our arrow like that. And then the leaving group, our halogen or whatever, will just leave. And it will take both electrons of this bond. Note, the lone pair on the nucleophile becomes a bond between the nucleophile and this carbon that contained the halogen. The halogen leaves with both electrons. And so then we have substituted. R now has a nucleophile attached to it, and the halide ion is gone. Note, the nucleophile is an electron pair donor, a Lewis base. The alkyl halide here is an electron pair acceptor, a Lewis acid. So this is a Lewis acid-base reaction. All of these reactions we're going to be talking about are Lewis acid-base reactions. Okay. Note, they are not Bronsted acid-base because there's no protons involved at this point. This is just a nucleophile attacking a carbon. There's no protons being transferred, so these are not Bronsted acid-base. They are purely Lewis acid-base reactions. So here's some examples down here. Say you have CH3CH2CH2Br, propyl bromide, and you put in sodium hydroxide. Well, the hydroxide has lone pairs on it. One of these lone pairs can attack and form a bond with this carbon, the carbon attached to the halogen, and then that halogen breaks off at the same time to give CH3CH2OH plus NABR. But note what we have done in this substitution reaction. We started with an alkyl halide, we end with an alcohol. So this substitution, one thing it can do is convert alkyl halides into alcohols. Let's see right here. What if we had CH3CH2Br and we reacted with OCH3 minus? Fix this up here. What we would get is the oxygen of this OCH3 minus. Note, HOCH3 is an alcohol, methanol. The conjugate base of an alcohol is an alkoxide, so this would be methoxide. So this methoxide is the nucleophile, attacks the carbon that has the bromine attached to it because this carbon is positively charged because the bromine's electronegative. So this oxygen attacks that carbon, the bromine takes its 2 electrons and leaves to give us CH3CH2OCH3, CH3CH2OCH3 plus Br minus. Something to notice, the nucleophile does not break up. When this attacks, the nucleophile does not leave any atoms behind. Okay, OCH3 stays as OCH3 in the product here. OH stays at OH. Note, remember, sodium is always a spectator ion. Sodium doesn't really get involved in this. It's just a spectator ion, so it's not part of the reaction. It's just sitting there watching. How boring is sodium? All right, so here we have this methoxide attaches here. So note, we've now taken this alkyl halide and converted it into an ether. CH3CH2OCH3 is an ether. We're changing the functional group. Look right here. CH3CH2CH2Br plus NCH33. Note, this guy has no charge to it, but it still has that lone pair. It makes a decent nucleophile. Lone pair attacks the positive carbon, partial positive carbon, bromide leaves. You get CH3CH2 N plus CH33 plus Br minus. Make sure you keep your charges and make sure all groups originally bonded to the nucleophile stay with the nucleophile. This had an N nitrogen and 3 methyl groups on it. It still has a nitrogen and 3 methyl groups on it. However, there is something interesting that happens kind of related to these reactions. If the substitution product has a positive charge, note here the product, the organic product here, we're not worried about the sodium. The organic product had no charge, the organic product had no charge here, the organic product has a positive charge. Okay, if the substitution product has a positive charge, but also a hydrogen on the nitrogen or oxygen, we will usually get deprotonation, proton transfer reaction to form a neutral product. Now, if we look at this nitrogen, are there any hydrogens bonded to it? No, this nitrogen does not have any hydrogens bonded to it, so it's going to stay like it is. But let's look at this reaction down here. Say if we have our propyl bromide again, we add some NH3, we're going to add some excess NH3. Why that? We'll see in a minute. Excess NH3 is necessary. But the lone pair will attack the partial positive carbon, the bromide would leave, which would leave us this beast here. CH3, CH2, NH3. Note this nitrogen has positive charge, but it has a hydrogen on it. It has 3 hydrogens. It has to have at least 1 hydrogen on it. So we're up at this rule. If a substitution product has a positive charge, yes, but also has a hydrogen on nitrogen or oxygen, yes, hydrogens on nitrogen, we'll get a deprotonation reaction to form a neutral product. The extra NH3 will act as a Bronsted base, come in, snag this hydrogen, the nitrogen-hydrogen bond will break, both electrons will go on to the nitrogen, and we'll end up with CH3, CH2, CH2, NH2, and this lone pair came from this bonding pair. This hydrogen's now on the nitrogen, NH4+. So this deprotonation reaction will always occur whenever your product of substitution has a nitrogen or oxygen with positive charge, and also that nitrogen or oxygen has hydrogens on it. Okay. Now let's pay a little attention to this group that leaves, our alkyl halide. We've been looking at those as leaving groups. They're very common leaving groups, as we're going to see. But what is the deal with leaving groups? All right. The leaving group, in order to get it to leave, this group must be kind of stable on its own. When we look at these reactions here, we know that bromide is fairly stable. Chloride, bromide, they're very stable ions. Sodium chloride, very stable molecule. You put it in water or whatever. Chloride is very stable. The leaving group, when it leaves and takes the 2 electrons with it, must be a kind of stable beast. The more stable the leaving group is, the better it can exist on its own, the more able it is to accept the electron pair when the bond breaks, and the more likely it is to leave. Well, what makes things more stable? What makes a leaving group more stable? When you look at it and you see that it is a weak base. The weaker the base, the leaving group is, the better it is as a leaving group. The weaker the base, the better the leaving group. So note, iodide, bromide, chloride, those are really weak bases. And therefore they are very good leaving groups. Water, that's not too bad of water's pretty stable, so it makes it a pretty good leaving group. NH3, well that's a base. And so that's not the best leaving group, because it's a base. And what do bases want to do? They want to take in protons. Water, does it want to take in protons? It can, but it's neutral. It doesn't really care. It'll take protons if you make it, but it doesn't care. So it's an okay leaving group. NH3 is not that good a leaving group because it wants to take protons. It's a stronger base. And so, wait a minute, but how do you know if it's a strong base? How did I know that these were weak bases? We have to look at the conjugate acid. So here's a nice table here where we look at, okay, a good leaving group is a weak base, and we know the conjugate acid of a weak base is a weak acid, but the weaker the base is, the stronger the acid. Remember, the stronger the acid, the weaker its conjugate base. So if we're looking at how good a leaving group, here's a chlorine, a bromine, an iodine, an OH2 plus attached to an R group. We know that this chlorine is neutral, but when it takes both electrons, if it leaves, it will be leaving as chloride. How stable is chloride? Well, we ask ourselves, what is the conjugate acid of chloride? Well, the conjugate acid of chloride is HCl. We know HCl is a strong acid. If it's a strong acid, its conjugate base is a very weak base. And we know it's a strong acid because the pKa is -7. So we know chloride is a very weak base. Therefore, it is a very good leaving group. The weaker the base, the better it is as a leaving group. Bromide, iodide, all very weak bases because they are the conjugate base of strong acids. But note this, that Ri, if you have an alkyl iodide, that makes iodide the leaving group. Hi is a stronger acid than HCl, which makes Hi makes I minus a really good leaving group. It turns out iodide is a super good leaving group because I minus is a weaker base than even chloride is. Right, and here's OH2, H2O. If we have this beast here and it leaves, it's H2O. The conjugate acid of H2O is H3O plus, pKa -1.7. So anything that's a good leaving group means it has a conjugate acid that has a negative pKa. If your conjugate acid of your leaving group has a negative pKa, it's a good leaving group. Well, let's look at some poor leaving groups here. F, fluoride, is really not that good of a leaving group because the F minus is pretty decent. It's a weak base. And it wants to take in hydrogens. HF is the conjugate acid, pK of 3.2. OH minus, horrible leaving group OH minus is, because OH minus is a strong base. It wants to take protons. The conjugate acid of OH minus is H2O, pKa is 15.7. All these guys here are extremely horrible leaving groups. They are strong bases. Good leaving groups are extremely weak bases. These guys are all extremely strong bases. Look at these pKa's of the conjugate acid. All right. So at this point, it'd be a good idea just to memorize, here are good leaving groups, here are poor leaving groups. And note, OH minus to R minus are very poor leaving groups. F minus, not a good leaving group. I'd classify it as poor, but it's a better leaving group than OH minus is. Look at pKa's here. It's closer to negative 1.7 than it is to 15. So while fluoride's not a great leaving group, it's kind of poor, but it's not nearly as bad as hydroxide is. All right. But here's the deal. These are weak bases. These are fairly strong bases. Strong bases make good nucleophiles. So when you're doing a substitution reaction, the thing to remember is that the equilibrium favors the products of a nucleophilic substitution when the leaving group is a weaker base than the nucleophile. Because note, the leaving group is a base, we want it to be a weak base. The nucleophile is a Lewis base, we want it to be a good Lewis base, a strong base. So when we look at this reaction here, we can see, all right, here's CH3, CH2Cl, and OH minus. So if we say we're going to do a substitution, all right, OH minus comes in, kicks off Cl, which gives us CH3, CH2OH plus Cl minus. And we could ask, well, wait a minute, Cl minus has got lone pairs on it. Couldn't it be a nucleophile? Attack this carbon and kick off OH minus? Well, it could, except how good of a leaving group is chloride? Very good leaving group. How good of a leaving group is hydroxide if the reverse reaction came about? Hydroxide's extremely poor leaving group. So, when we look at this, we find out hydroxide is a strong nucleophile. Chloride is a very weak nucleophile. Hydroxide's a strong base, chloride's a very weak base. Equilibrium favors it when the leaving group is a weaker base than the nucleophile. So the leaving group here being chloride and the nucleophile being hydroxide means that these are going to be the reactants and the products are over here. The products are going to be the alcohol and the chloride because chloride makes a good leaving group. If we try to run the reverse reaction, hydroxide, very poor leaving group. All right. So the last thing to our, well, continue on a little bit, nucleophile versus bases. Note, when we're doing a nucleophilic substitution reaction, go back to the previous page, we noted that it's a Lewis acid-base reaction. There's no protons being exchanged here. This is Lewis acid-base. So all of these strong nucleophiles here are also strong Bronsted bases because, note, pKa's are all about how strong a base is as a Bronsted acid Bronsted base. This is Bronsted acid base strength. The question is, what does Bronsted acid base strength, pKa's here, have to do with how good a nucleophile you have? So what is the relationship between nucleophilicity versus basicity? Usually a strong base is a strong nucleophile. The phrase that usually goes along with this is nucleophilicity parallels basicity. Strong nucleophiles are strong bases, weak nucleophiles are weak bases. usually, which means you can tell how good a nucleophile something is based on how good a Bronsted base it is, and you can use pKa's to tell you how, of the conjugate acid, to tell you how strong the base is. pK of -7 means HCl is a strong acid, which means chloride is a weak base. pKa of 38 means NH3 is a very, very, very weak acid, which means NH2 minus is a very, very strong base. So, this now becomes very important, this whole nucleophilicity parallels basicity, because it turns out pretty much almost all organic reactions are either Bronsted acid-base reactions or most of them are Lewis acid-base reactions. So if you want to understand why this organic reaction happened, well, it's a Lewis acid base. It's electron pairs being donated, nucleophiles reacting with positive charge. If you understand that the nucleophile, how strong it is, depends on how strong a acid, its conjugate acid is, in a Bronsted sense, then you will understand your organic reactions much better. So these pKa tables that I had you memorize in Chapter 2 are very, very important because not only they tell you how strong a base something is, that also tells you how strong a nucleophile it is, which tells you how strong a Lewis base it is, and almost all organic reactions are Lewis base and Lewis acid reactions. Okay, we will continue. We'll pick this up again in the next video and continue on.